time-dependent perturbation theory we have done so far is ready to be used. For example, we could propose some pulse in time that was perturbing some system, and we could calculate the results that we would get out of that. A particularly useful example case, though, is for oscillating perturbations, and very often time-dependent perturbation theory is used to treat exactly these kinds of problems. So we could be imagining then an oscillating perturbation that is perhaps varying sinusoidally in time, and we could call that a harmonic perturbation, with harmonic used in the same sense as in a harmonic oscillator. A good example would be a monochromatic electromagnetic wave, with an electric field in, say, the z direction, and possibly in a form like this. So here we have a cosinusoidal variation in time on the right, and we've written that in terms of the sum of two complex exponentials, which will turn out to be a very convenient way to separate this. And we have an amplitude for the field out the front here. Here, omega is chosen to be a positive number, positive angular frequency, and we will consider this here in first-order time-dependent perturbation theory. So with our field that we've just set up here, we presume it's going to act on an electron, and that will give the electron an electrostatic energy in this field relative to some position z equals 0, and consequently we'll have a perturbing Hamiltonian that would take this form. So the magnitude of the perturbation would be the magnitude of the electronic charge times the electric field times the position z. That corresponds to an energy, so we could say that's our perturbing Hamiltonian, and we'll write it out in this form where we have this function of time here multiplying some other perturbing Hamiltonian expression that is just independent of time. This hp0 is just this here, but only the magnitude of it, E times the magnitude of the field, the amplitude, times the position. And this particular operator, of course, is time independent, and it will come up when we're taking matrix elements later on with respect to the time-independent energy eigenfunctions. This perturbing Hamiltonian in this form, incidentally, is called the electric dipole approximation. Now, to set this problem up, we're going to presume that this perturbing Hamiltonian is only on for some finite amount of time. So we presume that it starts at time t equals 0 and ends at time t equals t0. So formally then, this Hamiltonian can be written as something that is 0 before time equal to 0 and is 0 after time equal to t0, and in the middle, in this time range here, it takes on this form we've just set up. We are interested in the case where, for times before t equals 0, the system is in some specific energy eigenstate. So this is going to simplify our starting condition for the problem. We don't have to choose this, but it will make our problem simpler to work with, and it's a typical case to analyze anyway. So time-dependent perturbation theory will tell us with what probability the system will make transitions into other states. With this choice of starting state here, all of the initial expansion coefficients, an 0, the zeroth order ones, are 0 except for this one particular one, which will of course be 1. So saying we start out in this particular energy eigenstate before we turn on the perturbation is the same thing as saying that am0 is 1. With this simplification of our initial state to just psi m, the first-order perturbation solution is quite straightforward. We have this equation here now, and only this one coefficient is going to be 1. And so the summation just reduces to one term. And so here's our equation for the time variation of the first-order correction to the wave function for state q, the contribution from state q. It's just this expression here. And of course, this expression is quite easy to work with. We're going to substitute our perturbing Hamiltonian in here, which was this one. And with that substitution and integrating over time, from time 0 to time t0, we're going to have this integral here to evaluate. So we're just writing this out here. Here's our matrix element between these two states, the initial state psi m and the state of interest psi q of a perturbing Hamiltonian. And we can separate that out into our time-independent part here and just leave all of these other terms here from the time dependence that was built into the field. So we've got two exponentials here, two complex exponentials. And of course, integrating these over time is quite straightforward. So for times greater than t0, once we've turned off the perturbation, that means we've integrated from time 0 to time t0. Well, at time 0, these complex exponentials were just unity, and at time t0, they're this amount here. And of course, we acquired this denominator from the process of integration. And we've got two terms, one like this and one like this, one with the minus sign in here and one with the plus sign in here, from the e to the minus I omega t and from the e to the plus I omega t in our field. And we can rearrange that slightly. We can take out a common factor here from both of these terms, for example, and that then leaves us with a sign expression from this minus sign in here after we've taken out this common term with the 2 on the bottom line. And similarly, we can do a manipulation on this term to get this form here. We like this form because these are basically sinc functions, sin x over x functions, that have specific simple physical interpretations we can put on them. So we've got two terms, one with this sinc function, one with that sinc function. Well, this function, the sinc function, sin x over x, is a function that looks like this on this red curve here as a function of the variable x. We've also plotted the square of that, since that will come up later on. And this function peaks at 1 for x equals 0, but it's only really large in the vicinity of the middle of this graph. As we go out to larger negative or larger positive arguments, it falls off pretty quickly and it never comes back. So this is only large in the vicinity of x equals 0. That means that, for example, this particular sinc term, which we saw in our previous equation, is strongly resonant. That is, it only has strong contributions when the frequency omega is close to the frequency omega qm. This is the frequency of the field, and omega qm is the frequency corresponding to the energy separation between level q and level m, where level m is the energy we started in. So now we have calculated the new state for times t greater than t0 here, which is, to first order, this expression here. So this is our original energy eigenstate of the unperturbed problem with its time varying factor. And then the change in the wave functions is the sum over all of these AQ1s that we now know how to calculate for times greater than t0, that is, the ones that we get to after we've finished with the perturbation, again times these various eigenstates with their complex exponential time factors in them. And we have now established, therefore, our approximation to the new state. And now we can start calculating the time dependence of measurable quantities.